Everyone.
Good morning, Acha.
Do you have any questions about anything before I start lecture today? No? Okay. Last time I showed you how to get the solution for field bending problem, right? Okay. Today I will move to the basic problem in the class of Saint Vernon problems. Okay, we'll talk about the field torsion problem. So in this particular case, I will look at a cylindrical body with the circular cross section. Okay, so the cross section here is circular, not arbitrary anymore. Okay, let's say that okay, at the left and at the right end, we apply the traction such that the net force at the left end is 0. Okay, so we apply any traction. I don't have any specific distribution of the traction. I just said okay, the traction that I apply at the end, at the left end, has no net force. Okay, so F0L is simply 0. All the components are 0. Okay, but if you look at the net moments, okay, we have one component that is non-zero, so we call M0L3. Okay, the third component or the component direct along x1 axis. Sorry, x3 axis. Okay, so that moment generate the twist to the body that we consider here. Okay, so all we call this is a torque. Okay, apply at the left end. So this is simply the net moment that we have for that particular for that traction T0L. Okay, so there are several distributions that possible to generate this kind of net force and moments. Okay, at the right end, we look at the traction as well. The traction at the right end may have different kind of distribution. Okay, but the net forces and net moments that generated at the right end is of the same form like this. Okay, so the traction that we apply at the right end generate no net force. Okay, and the net moment is simply 0, 0, and t. Okay, t here is the specified resultant moment, or we call the torque. Okay, so you can see that for equilibrium of the whole body, so the net moment that we have at the right end have to be the same but opposite in direction, right? To maintain the equilibrium of the whole body. So M0L here is you know opposite to M0R. Okay. So now I replace the traction with the net forces and moments like what I show in the figure here. So the simplified problem that we look at here is simply the one that represent a big classes, a big class of problem. Okay, any kind of traction that generate the same net forces and moments here will classify as the same problem in the Saint Vernon concept. Okay, if we don't care much about the solution near the ends of the body, we focus only on the solution in the interior zone. So all those problems are considered to have about the same solution. Okay, so and that solution can be obtained by the simplified Bari value problem. We just simply replace the distribution of the traction by the resultant forces and moments. Okay, but here the moment that we look at, we have only the component along the axis of the body. So we call the torque. Okay, this is simply the pure torsion problem that you learned before in structural material class in your undergraduate level, right? So you know how to get stresses that induce inside the body, right? So typically when you apply the torsion at both ends, it will generate the shear stresses, right, at any point in the cross section. And you can compute the shear stress. If you remember, the shear stress is simply T multiplied by R divided by J, right? That is the formula that we call the torsion formula. So that should be well known to you guys here, right? So if you want to compute stress at any location, you just simply use that formula. That is what we got in that basic class in strength of material, right? But here we try to investigate the same problem again in the context of solid mechanics. Okay, I don't know exactly here that okay the solution going to be the same or different, because we look at the problem in based on different kind of governing equation. Okay, so we look at the governing equation in the context of three-dimensional settings. So here, let's see. Okay, how can we get the solution? So I would not solve the problem directly again, but I would try to change the strategy that I used for the two problems that I considered before. Okay, before we try to guess straight field, right? For both cases that we look at before. Okay, for the pure tension problem, pure bending problem, we start by guessing straight field based on the information that you learned before in strength of material class, right? But here I will try to do in different way. But I didn't say that okay, guessing the straight field is not okay for this problem. You can still do the same way in the same way, because based on strength of material class, you know that okay, shear stress should be equal to TR over J, right? So maybe that may be a good choice for the starting step, right? You can guess straight field in that particular form and follow the same kind of procedure that I showed you before. But here I will try to look at the way to solving the problem in different directions. So this is also possible. I will show you how to get the solution for this problem by guessing the displacement field. Okay. So to do that, I have to think about the form of the displacement field for this particular problem. Okay. So this is the difficult part. Okay. Once you come up with the good choice or the right choice or the appropriate choice of the displacement, now you can go ahead and check or even determine the constants that involved in the form that you guessed. This should be similar to the exam, the exam problem that I asked you before, right? Or similar to one of the problem that you have to solve in your homework assignment. Okay, so the more difficult part is guessing, the displacement field in a good form. But here, I will guess the displacement in this particular form. Okay, I say that okay, the displacement we have only U1 and U2, and we assume that okay, there is no U3. So when we try to apply the torque at both ends, so it just simply rotate the cross section. We think about in that way. Just say that okay, the torque that we apply here just simply rotate the cross section, and the cross section itself remain the same without changing the shape of the cross section. So it remains circular before and after applying the torque. Okay, it just simply rotate from the original configuration. So in that particular case, there is no movement along the axis of the cylinder. So we say that U3 is 0. So that's what I guess based on my intuition. So I think that, okay, the displacement should take this particular form. Okay, and C1 and C2 are unknown constants to be determined. Okay, so if you look at the displacement field, you can see that U1 and U2, the form that I guess here is not linear. Okay, it's not linear. Why I come up with this form? So this is what I use, to get the form of U here. So I use the knowledge based, knowledge from the basic class that I learned before, or you can do in the same way, because we assume that, okay, there is no movement of the cross section along the axis, so that we say that, okay, there is no warping displacement. The warping displacement is the out plane displacement. Okay, the displacement that normal to the cross section of the body here. So we assume this. We don't know exactly that is correct or not, but it's a good way, to assume, because if you look at the torsion that apply here, if you make a cut at any cross section, you see exactly the same net torsion applied to the cross section. So because of that kind of thing, so I can say that, okay, there shouldn't be any movement in the axial direction, because you see exactly the same thing when you make a cut there. So I guess I guess that, okay, the displacement U3 have to be 0. I will check it later that the assumption that I made here is correct or not, because at the end, if the displacement field that you guess here can satisfy all the requirements, so you can say that this is the right one, right? And also, I assume that the displacement should be linear in X3. Do you have any explanation for this? Why I think that, okay, the displacement should be linear in X3? Can anyone tell me here? If you take a look at the form that I guess here, in terms of X3, you can see that both U1 and U2 are dependent on X3. So we can say that they are linear in X3. Do you have any idea why I assume this? Think about this. If you think about that, you hold the left end of the bar and you start applying the torque there. So let's say that for simplicity, you can just imagine that at the left end here you hold the bar fixed. Okay, now you apply the torque at the right end. So when you start moving from the left end to the right end, you can see that the rotation of the cross section keep increasing, right? Okay, there's no rotation at the left end, and the maximum rotation of the cross section should be maximum at the right end, and in between it should be linear in X3. So the rotation of the cross section somehow proportional to the displacement that occur in the cross section, right? So in that sense, so I assume that displacement should be linear in X3. Okay, and also I assume that U1 should be linear in X2 as well, and U2 should be linear in X1. How can I come up with this idea? If you think about the rotation, if you think about the rotation of the cross section, if you try to rotate the cross section at any coordinate X3, let's say that you fix the coordinate X3, the cross section just rotate, right? When you apply the torque, it rotate. What happened to the rotation there? So if you make the cross section rotate, the displacement will get larger and larger when you move from the origin of the cross section, right? If you move from the center of the cross section, the displacement become larger and larger, right? Think about that. Because when you rotate the cross section like this, so the displacement U1 and U2 should be 0 at the center of the cross section, right? And it should be larger and larger when you move far away from the center of the cross section, and should be maximum at point on the boundary. So you can see in that sense. So the displacement should be linear with respect to the distance from, from the center of the cross section. Now, when you look at the component U1 and U2, so because the displacement is linear with respect to the distance from the center. So if you look in terms of U1, the component U1 in X1 direction, it should be linear in X2, right? Right. You can go back and sketch the figure and see why I made the assumption. The reason because when you move far away from the center of the cross section, the rotation that generated for the cross section will produce linear components of in plane displacement U1 and U2, linear in X1 and X2, right? In this way, okay? So based on this idea, I come up with this displacement field, okay? This is based on my intuition, okay? An assumption that, okay, there's no warping displacement for the cross section. So it's a little bit more difficult if we work out this problem by assuming the displacement field or guessing the displacement field compared with guessing the straight field, right? Because if you get a straight field for this particular problem, you can use the one that the formula that you are familiar with for torsion problem. You know that, okay, that the torsion will generate the shear stress components in the cross section using the formula TR/J, right? So if you have that kind of sense, so working out this problem in terms of guessing, in terms of straight field, the guess straight field, it may be easier. Okay, but here I try to provide you a different way, to get the solution for this particular problem. I didn't try to to say that, okay, this is the easiest or the simplest way to get the solution. It's just one way that I can get the solution. Okay. Do you have any question about anything here? So whenever I come up with the guess displacement field, the rest should be simple. Okay, I just simply follow the same procedure that I did. I showed you before in the previous lecture, right? If we start by guessing the displacement field, so now you know all the conditions that you have to check to ensure that the guess displacement field here can be the solution of the problem, and also the constants that you introduce in the guess form there can be determined. Okay. Now, I generate strain field from the guess displacement field. This is the way that I think it's simple, because if you try to check Navier equation, that is one way that possible. But here, I will not try to do in that way. I try to generate all the remaining fields, and then I check all basic equations. Okay, so I start using this relationship, strain displacement relationship. I start to use this one to generate strain. Whenever I generate strain out of this relationship, now I can say that these equations are satisfied automatically via the generation of the strain field. I don't need to check this equation again, because strain is generated by these equations. Okay, so I just simply plug in the guess displacement field. Okay, so I plug it in. I come up with this a strain tensor. Okay, so I didn't show you in detail how to get all the components here, because it's just simply taking the derivative and plug it in here, right? So that should be straightforward. Okay, everyone here should be able to do to come up with this strain tensor, right? Okay, so then once I get strain field, I can plug in strain relationship, right? So I have all the components of strain tensor. Now I can get stress components easily by simply plugging all the component here into this commutative law, right? So I plug this thing in, I get this final stress tensor. Okay, so strain and stress that I got here are given in terms of the constant C1 and C2 and some of the material properties and and the coordinate x1 and x2. You can see that strain and stress are not constant for this particular case, and they are linear function, right? So if you look at each component, you can see that strain are either 0 or linear function of x1 or x2 or x3. You can see that. Okay. Okay, now I generate the 2 remaining fields from the gauge displacement, right? So I can say that 2 equations, 2 sets of equations here are satisfied automatically. So if you try to verify all the fields that we have here, we need to check all governing equation, right? So it still remains to check the other set of equation, the equilibrium equation. That is the last one that you have to check for point inside the body, right? So I will look at the equilibrium equations for this particular problem. So this is the form of the equilibrium equation. This is a general form. And for this particular problem, we know that Bi is 0 because we don't have body force field. Okay, so now we just need to verify that the divergence of stress field sigma I j comma j here, we need to verify that have to be 0. So for all free index I from 1 to 3, right? So this is stress field that we got. B is 0. So now I can check one by one, right? So we have 3 independent equilibrium equations. We just simply plug in I equal to 1, I get the first equation, and I equal to 2, I get the second, and so on. So you can see clearly, for example, for the first equation, when I equal to 1, you get the term like this: sigma 1 1 comma 1, sigma 1 2 comma 2, sigma 1 3 comma 3 plus. Okay, you combine all the term here, you get 0. But B1 is 0 because the problem that we are interested in here, subject to the body is subject to the 0 body force field. So B1 is 0, and if you take a look at the first row of the matrix here, so sigma 1 1 is 0, so that term disappear, and sigma 1 2, even though that one is not 0, but we take derivative with respect to x2, but this is linear in x3, so derivative of that term with respect to x2 is 0. And that one is 0 too, because you have to take derivative with respect to x3. So you can see that all the term here are 0. Or I can say that this equation is satisfied automatically. Okay, I can do exactly the same way for the second one. Okay, I see exactly the same thing, and the last one as well. Okay, so you can go back and look at all the terms that we have. So now you can see why I say that all the equations are satisfied automatically. So what does it mean? It means that the displacement field that I gave there satisfy, or the displacement field that I guessed. Once you generate strain and stress, okay, all fields that you have here satisfy all governing equations. Okay, so now I don't need to worry about the governing equation for point inside the body. We check it already. Okay. The last, we have to check boundary conditions, right? So that is the most important part. Okay. So first we look at the side face. Okay, the boundary condition on the side face. If you remember, on the side face, we have to check the traction condition at every point. Okay, so we hope that the field that we generate there can satisfy this condition automatically. Okay, because we didn't look at the net force or moments anyway for this surface. So we just simply enforce the original traction boundary condition directly. Okay, so now one thing that I have to emphasize here, we know that okay, the cross section of the body is circular, right? So we just look at the problem with the body with the circular cross section, not the general cross section for this particular case, because for the torsion problem with arbitrary cross section, the problem is quite complicated. So if you remember correctly, in your class, in the strength material class, you focus attention mainly on the cross section is circle, right? Okay. So in this particular case, we got some important information regarding the unit normal vector, right? So if I look at point x1, x2 along the circumference of the circle, let's say that okay, the radius of the circle is r. Okay, so now I can use the geometry of the circle to conclude that okay, the outward unit normal vector at any point x1, x2 on the circumference of the circle is simply the vector x1 over r, x2 over r, and 0. It's quite clear that because the body here is cylinder, right? So n3 have to be 0 because all the cross section are exactly the same, are identical. So we cannot have n3. And n1 and n2 have to lie along with the line connecting the center of the circle and the point that you consider here. So n have to point in the same direction. So we just simply scale x1 and x2 by r to make sure that okay, n here is of unit magnitude, right? So that is the unit normal vector for this particular circular cross section. Okay. So based on that information, now I can check the traction at every point on the side face. Okay. So computing the traction is simple. We just simply take the product between stress that you generated before, right? And you multiply that tensor by our unit normal vector that we got for the circular cross section. So we take the multiplication there and we get something like this. Okay. Is that clear to you? Is that clear? Okay. Now, we know that okay, the traction on the surface S part or on the side face, we need the traction to be 0. All the components have to be 0, right? So if we take a look at the form that we got here, so T1, T2, and T3, they are not 0 here. They can be 0 only for the case that C1 plus C2 is 0, right? Is that clear to you? Because the material constant is not 0 and the coordinate here are arbitrary. So the only way that the whole thing here disappear, C1 plus C2 have to be 0. Okay, so now I can say that the boundary condition on the surface S pi can be satisfied if C1 and C2 here are not independent, but C1 plus C2 have to be 0. Okay, or I can say that C1 is simply the negative of C2. Okay, so if that is the case, now the boundary condition on the side face is satisfied. Okay, so based on the enforcement of the boundary condition on the side face, I can say that I can reduce from 2 unknown constants to a single constant, because C1 and C2 now they are not independent, right? So C1 and C2 are dependent, and C1 can be expressed in terms of C2. So I reduce the number of unknowns from 2 to 1. Okay. So now we should C1 equal to minus C2 equal to negative C. And C here is the representative constant after we satisfying the boundary condition on the side face. Okay. If we choose C1 equal to minus C2 equal to minus C, so now the boundary condition on the surface S pi are satisfied, and now we can reduce the gauge displacement to be the form here. Okay, instead of have C1 and C2, now I express C1 and C2 in terms of C. Okay, so now I get the form like that. C is still unknown, right? We have to determine this constant as well, but don't forget that, okay, we still have the condition at the left and at the right ends to be enforced, right? Okay, now I just make a summary here first before we go to that point. I try to reduce the unknown constant to, C. Okay, I try to get the form with only one constant here. So this is summary after we enforce the conditions on the surface S pi. Okay, so we have displacement field, strain field, and straight field like that. Okay, next I move to check the boundary conditions on the surface S1. SL. Okay, at the left end of the body. Again, I will not force the traction boundary condition at every point here. Okay, I will try to satisfy the boundary condition in average sense by satisfying the net force and moment, right? Okay, so I start computing net force and net moment at the left end generated by stress or traction that I got before. Okay, because the net forces and net moments that prescribed due to the traction I apply at both ends, I got that already, right? So the one that I show here are net forces and moments at the left and at the right end. So I know the one that prescribed. Now I have to confirm that the net forces and moments generated by stress inside, when we move to the left end and the right end, we get exactly the same net forces and moments. Okay, so I will start by computing the net forces and moments at the left end. Okay, I still use the same formula if you remember. Okay, I gave you the formula to get FL, okay, in terms of stress component. I just simply plug in sigma 1 3, sigma 2 3, and sigma 3 3 into this formula, and we know that sigma 3 3 is 0, right? From stress field that we got before. So sigma 3 3 is 0. So the third term or the third component here disappear. Sigma 1 3 and sigma 2 3 are not 0, right? So I plug that thing in, I get like this, and I just pull out the constant mu and c from the integral because they are constant. Okay, so I come up with this. Okay, so it's quite clear here that the integral that we have there vanish, right? Because the origin that I showed there is at the centroid of the cross section, and here for this particular case it's at the center of the circle. So the integral here should be 0, right? Okay, because of the definition of the centroid, so that term disappear and that term disappear. So now I end up with what? I end up with 0 net forces in all directions, right? And that should be clear that, okay, it's identical to what we prescribe there, right? So FL here is exactly the same as FL0 from the traction. So now I can say that at the left end, the net force condition are satisfied automatically. Okay, it doesn't matter what the value of C is. Okay, so now I move to check the net moments as well. So I have the formula for the net moments. So I plug in the stress component back into the formula in the same way. We know that sigma 3 is 0. So the first term here disappears and the second one as well. But sigma 2, 3, and 1, 3 are non-zero. So I plug them in here. So finally I come up with this result. Okay, the first two components disappear. That should be clear, right? And the last one, once I plug in sigma 1, 3 and sigma 2, 3, so I come up with this expression. I just move the constant out of the integral, and the term inside here is simply the integral of x1 squared plus x2 squared. But if you remember, in the first part of this lecture, I talked about this quantity before, right? If you remember, okay, can you remember? So the integral of x1 squared plus x2 squared over the cross section is simply what? It's simply what? Polar moment of inertia, right? Right. This is the polar moment of inertia of the cross section, right? So I plug that in because J here is simply, simply the property of the cross section. Once you know the cross section, you should be able to get J. And for this particular cross section, it's circle, right? So the cross section is circular. So now you can get J easily. Okay. So now I get the net moment like that. If you compare the thing that you got here, this is the one that generated by straight field, right? At the left end. And compare with the one that you got here, that is the one that prescribed, or the one that calculated from the prescribed traction, right? Okay. So if you compare them, you need to get the same values, right? For both term here, because you want to make sure that okay, the net moments are the same to satisfy the condition at the left end. So when you directly compare all the components, the first and the second, they are the same. They are 0. So if we look at the last term, they are not exactly the same, except the value of C here is chosen. It's chosen in a special way, right? So if you get the C that make the term here the same as that term, now you're done, right? So you can say that I can pick the value of C to make sure that the two vectors here are exactly the same, or you can choose the value of C to make sure that the condition at the left end are satisfied. Okay, so I can pick C equal to T over mu J. Okay, if you pick the value of C, the constant C, equal to T over mu J, now you know that okay, the moment, the net moment ML generated by straight field and M0L generated by the prescribed traction T0L are exactly the same. Or I can say that with this value of C, the boundary condition at the left end are satisfied in the average sense. Okay. Up to this point, do you have any question about anything? Okay. Now it seems that we already got all the unknown that we need, right? We get C. Okay, so now we get everything. We can say that, but it still remains to check the right end. You cannot stop here without checking the condition at the right end. You cannot say that okay, now I get all the constants I need, so now I will stop. I will not check the remaining conditions. That is not right, because it may be possible that the C that you got here is not the correct one. And also the form that you get may not be the solution. Because if you move to the right end and you get the value of C that different from here, or you check that, okay, with this C, you cannot satisfy the conditions at the right end. So what happened then? Now, the form that you get at the beginning is not the right solution. You know what I mean, right? Okay, so we cannot just simply stop here. We need to check on all the conditions that we have. It still remains to check the boundary condition at the right end here on the surface SR. So in this case, I can do exactly in the same way, okay, except that, okay, I look at the right end. So I use the formula for the right end and follow the same procedure. For example, the net force at the right end can be obtained easily based on the same kind of formula, but you have to be careful about the side too, because for the left end, you have the negative side, but for the right end, you don't have it. So in this case, I plug everything in, and finally I can verify that FR is simply zero vector, okay? And this implies what? The condition on the net force is satisfied, right? Here, you can see that they are exactly the same. For the net moment, I compute the net moments from stress, and this will finally result in this. Okay, like that. So you can see that the net moment, the third component, or the torque generated by stress field, is non-zero. But the bending moment, M1 and M2, disappear. So I have only M3 that equal to mu Cj. I need to check that, okay, this one is exactly the same as that one, right? Okay, so it depends on the value of C again. Okay, from this case, we end up with this kind of conclusion, right? So we can see that the two conditions here, one is satisfied automatically. It doesn't matter the value of the constancy is, right? So the first condition, or the net force condition, are satisfied automatically. But the net moment can be satisfied only when C equal to Q mu J, or this constant is chosen for C. So now this condition is satisfied, right? So if you compare the value of C that you got here and you got from the left end, you are lucky that, okay, the value of C that you need to satisfy the condition at both ends are exactly the same. If they are not the same, now you have problem, because that implies something on the gauge displacement field, right? It may not be acceptable. But in this case, it seems consistent, because C that you got here and C that you got before are exactly the same. Okay, so now I am done with checking all the conditions. Okay, it seems that the C that I got here on the form of the displacement I have at the beginning is the appropriate one. Right? So let me summarize here. So now the conclusion is the gauge displacement field of that form, okay, satisfy what? Stress field that it's in equilibrium, right? So you generate stress and strain, and now you verify already that the stress is in equilibrium, and also satisfy traction boundary condition on the side face if C1 is negative of C2, okay? And if you want to satisfy the left end conditions, so you have to pick C1 and C2 equal to the, C1 is the negative of C2 based on the condition on the surface S point, and the value of that constant equal to TO mu J, came from the satisfaction of the boundary condition on the surface SL. The same thing for SR. So now I can say that the gauge displacement field is the solution of the problem, right? The solution of the simplified problem. Okay, if we should C1, C2, and C, or you can say the C1 and C2 are chosen to satisfy that condition. Okay. Is that clear to you? So now once I'm done with checking all the condition, I get all the constants that I need. Now I can generate all the field. Okay. Displacement is now known, right? It's like that because I plug in C1 and C2 there into the expression. So I get strain field as well. So plug in the constant, the same for stress. We done here. Okay. Is that clear to you? So now if you look at stress field that we got here, there's no normal stress. So they apply torque, just simply generate the shear components, right, for the stress tensor. So we have only shear component, and one shear component disappear. This one disappear. You can see that. So that is simply the in-plane. Sorry, the in-plane shear component. The in-plane shear component is 0, right? Sigma 1, 2. I term sigma 1, 2 with the in-plane shear component. If you take a look at the way that we name the coordinate system, the coordinate axis. So you know that sigma 1, 2 is simply the shear that try to distort the cross section in plane, right? So that one disappear, and sigma 1, 3 and sigma 2, 3 are non-zero, and that is the shear component appear on the cross section. So that is similar to what you learned from strength of material class, right? Can you remember? If you have the circular cross section like this, okay, if you apply the torque like that. So if you look at any particular point here, so you know that the torque that you apply there will generate what? Shear stress in that direction, right? You're gonna have shear stress in that. You're gonna have shear stress in that direction. So the direction of the shear stress is simply, you know, the direction that normal to the line connecting that point and the center of the circle, right? So the angle here have to be 90 degrees, right? Okay. So now that's what we call tau, right? In the class that you learned before, and this shear stress can be obtained from the basic formula that we call the torsion formula, right? It's simply TR over J, if you remember, right? Is that the one that you are familiar with, right? In the class มีใครไม่เคยเจอสูตรนี้บ้างมีไหมคุ้นเคยไหมสูตรเนี้ยว่าไงครับพวกเราเคยเรียนกันยังไม่มีใครตอบเลยโอเคครับโอเคดีมากโอเคครับOkay, now if we look at the shear stress that we got at any point on the cross section, now we can component that. Okay. So we can get the component like this, right? And we can get the component like that. And the two components that I mentioned here, simply this one simply what? That one should be what? Sigma 1, 3, right? And that should be sigma 2, 3. Okay, and that's what you get here, right? Because R is simply the distance here. Okay, so when you take the component, so that one you have to change R to X2, right? And you have to change R to X1 for that component. Because when you plug it in here, when you take the component, you're gonna have R cosine theta and R sine theta. R cosine theta become X1 and R sine theta become X2, right? So and that ends up with exactly the same shear stress components here. Okay, so what I try to summarize here, the thing that you got here is exactly the same as what you observed before in strength of material class. Okay, So the solution are exactly the same. That's what I can say. Okay. Do you have any question about anything here? Okay. Now I have a simple remarks here. Okay. If you would like to know the spatial, the spatial distribution of the traction both ends that will make the solution that you got before the exact solution of this problem, or if you would like to know the condition that the loading condition that you apply at both ends that make the solution for the simplified BVP to be exactly the same as the original BVP. So what should be the traction that you have to apply at both ends? Okay, to get that kind of information, I will do this. Okay, I will just simply I just simply generate the traction based on the stress that I got before, okay, and multiply by unit normal vector at the left and at the right end. Okay, so now I get the traction like this. Okay, so that is the traction at the left end. Okay, and at the right end I can get like this. So you can see that the traction that I need to apply at both ends have to be linear in x1 and x2, like the form that I showed there. Okay, if you look at the magnitude of the traction that I have to apply, the traction that I have to apply at the end have to be linear with respect to the distance from the center of the circle, right? So in the form that you got here is exactly the form as what you learned in strength material class. So what I try to say here, if you apply a shear traction at both ends linearly with the linear distribution, linear with respect to the distance from the center of the cross section, now you can say that if you apply the linear distribution of the shear traction at both ends to generate the torque T, the solution that you got will be exactly the same as the one that I showed before. Okay, so if you face with that kind of situation, now you can see that you can say that, okay, the solution that you got here is the right solution everywhere, including the end zone. But if you apply the traction at the end that different from this, but it still generate the same kind of net force and net moments at the end, what you can conclude? The solution that you got before is still okay if you look at the interior zone. But when you move to the zone close to the end of the body here, the solution will not be the same anymore. Okay? Okay? That's the conclusion. Okay. I will stop this lecture here. I show you all three basic problems in the class of Saint-Bernard problems. There are several remaining problems that you need to solve. Okay, or if you think about, okay, there are several kind of combinations that you can have for the net force and moment applied at the ends. You can have the combination of moment and forces. Okay, so the one that I show here is just the basic one. Okay, you can have the combination, like I say, at both ends. You may have moment acting at the cross section together with the force at the same time. For example, you can have the shear force and you can have the moment applied at the end at the same time. But the problem getting more complicated when you have that kind of mixed loading at the end, or the mixed condition of the net forces and moments. Okay, but the strategy that I recommend you to here may be applicable to those cases. So I will give one problem in the homework assignment, the last homework assignment for you to practice. Okay, how to solve the problem in this class. Okay, so I will stop here and I will move to the next, the last lecture 5. I post that in my course view last night. Okay, that note is still not complete. Okay, this is the third part of the note. Okay, I will try to prepare the remaining part. Okay, so I will give you about 3 minutes or 5 minutes, okay, to download that lecture in case that you haven't, check, the update of the note in my course view. I will be back in 2 or 3 minutes. Okay, please download the download the file from my course view, and I'll see you in a moment. Okay.